My name is Hegg, and for those of you, I just want to start out by saying that what I'm going to talk about is done in collaboration with Nathaniel Oster, who you just met, and also Nikolai Leinhardt, who's in the chemistry department at the University of Michigan. And you'll see why these two people are instrumental in what I do here in just a moment. But relating back to the question that was just asked, can you use isotopes to look at enzyme mechanism? And that's exactly what I'll be talking about today. That's my interest. There's two sort of uses two major uses, I would say, of the heavy isotopes. One is for tracing, and that you heard a lot about that today, and the other is for mechanistic work, and that's what I'll be talking about. So I'm an enzymologist, and so I'm interested in how enzymes work and what's the mechanism. And there's all sorts of ways to get to this. You can do spectroscopy, you can look at intermediates, you can do kinetics and all sorts of things. But sometimes you reach the end of what you can do, and you still have more than one possible mechanism that fits all the data. In this particular example, there's three possible mechanisms. And so what do you do at this point? And so another tool in our toolbox is isotopes. So for those of you who are familiar with it, why does it work? It works because you can think of all chemical bonds as a harmonic oscillator. The energy is simply given as 1/2 h bar nu, where nu, the vibrational frequency, is proportional to 1/the square root of the reduced mass. Right? So what that basically means is that heavy atoms vibrate more slowly. You can think of that very simply by, if you take a spring, two identical springs, and on one of them you attach them both to the ceiling, on one of them you put a bowling ball, on another one you put a baseball, you let them go, which one's going to vibrate more slowly? And the bowling ball is going to vibrate a lot more slowly. And because it vibrates more slowly, it means it has a lower zero-point energy, to put it in sort of simplistic terms. And so if this is a very simple reaction coordinate, if you're down here sort of in the reactant state, the heavy atoms will be in a lower ground state than the lighter atoms. And what that means then is if you have to go up and over the transition state, as a general rule of thumb, the light atoms have a lower activation energy than the heavy atoms. And if this is the case, then the light atoms react more quickly, and you get what's known as a normal isotope effect. Sometimes, however, depending on what the transition state looks like, you can have the inverse. You can have the case where actually the light atoms react more slowly than the heavy atoms. And all of this can give you information then about the reaction coordinate and what's going on in the enzyme mechanism. All right, so that's just kind of a big overview. The bottom line is that all chemical and biochemical reactions will have different preferences for one isotope over another. All right, so with that background, I'll give you an example that was just mentioned a moment ago, which is nitrous oxide biosynthesis. And so we were interested in studying it for the reasons Nathaniel already outlined. And so what we did was we simply ran the reaction using purified enzyme. We isolated the N2O, and then we measured the isotope values. And as Nathaniel already mentioned, there's two different nitrogens as well as the oxygen. You get the isotope ratio for all of these. And I won't bore you with the math here, but the bottom line is you can get something that's known as the kinetic isotope effect. In other words, what's the ratio of the light atom reacting versus the heavy atom reacting. And when we did that, those reactions and did the analysis, we obtained the numbers shown right here, which in and of itself doesn't really tell you anything, but you can see here that we've got the alpha nitrogen and the oxygen have a normal isotope effect, and the beta nitrogen has an inverse isotope effect. Okay, so what does that mean, and what do you do with it? So this is then where the collaboration with Nikolai Leinhardt becomes important, because what we have now is information about what is preferred. We still need to be able to interpret it. And so what Nikolai does is using a combination of DFT, intensive functional theory, and other types of calculations, he basically looks at the different potential reaction mechanisms and then calculates what the various activation energies are. And from that, we can get some idea of what the isotope effects would be if this mechanism were going on. And then when you do that, sometimes you find out, well, that doesn't fit the available data. And sometimes we get a question mark, which means, well, it's consistent with the available data, so we can't rule it out. Of course, you can never sort of prove a mechanism. You can only disprove mechanism. So this is where this is where it allows us to go. And we've had a lot of luck doing this so far with one type of nitrous oxide biosynthesis enzyme, and we're working on others. Okay, so what you see here then is everything I've talked about so far is nitrogen and oxygen. But the reaction is going on at the iron, right? And so far I've talked anything about the iron, the metal isotopes. And why is that? Well, the reason is because the difference in reduced mass, once you get to the heavy atoms, isn't big enough for you to be able to do these kinds of studies. And so you simply can't get the type of discrimination between the isotopes that you need. So I was sort of thinking, sort of blue sky, what could one imagine if you had access to all sorts of different isotopes that normally you wouldn't have access to? And so I thought about nickel-containing enzymes. I've been interested in some nickel enzymes for quite some time, and I show you some here, and the identity is irrelevant. But the point is, if you look at the available nickel isotopes, these are the two common isotopes, nickel-58 and nickel-60. You can see the relative abundances. There's not enough difference between them to be able to analyze the mechanism. However, if we were able to get some heavier isotopes of nickel, then in fact the delta, in other words the difference in the reduced mass that we would need, would be exactly the same or about half of what we're already doing the chemistry with when we're looking at the N2O. And so it would give us then another piece of the puzzle to figure out what's going on in the enzyme mechanism. So that's blue sky. This is an example of nickel, but you could imagine this with other metals as well. So that's it. Thanks.
A few questions. So there's a lot of interest in nitrogen. So in this beam dump, how much nitrogen isotopes might you produce?
Tons.
Tons?
Because it's water.
Yeah.
And so you know, curious of activity, but you have to get it out.
Yeah.
Nitrogen has N13 has a 20-minute half-life.
9.6.
Yeah, 10 minutes, sorry. So you have to work fast.
Actually, we did experiments together 30 years ago.
That's true. Yeah, when I first came here, yeah.
Yeah.
Okay, thanks everybody.